In this video, we're going to cover how to balance redox reactions. I want you to consider this reaction, and I want you to ask yourself, is this particular reaction balanced? Well, it looks like it is for mass. On this side of the equation, I have one copper, and I have one copper on this side of the equation. And if I look over here, I have a single silver, and over here I have a single silver. So we might suspect that this reaction has been balanced, but it's not. And the reason why it's not balanced is because in addition to a law of conservation of mass, which this equation obeys, there's also a law of conservation of charge, which this equation does not obey. Now if we look at this, copper is solid, that's an element, no charge, and so its oxidation number is 0. And then over here, also, silver solid is going to be no charge with an oxidation number 0. If I look at the total charge of the species on this side, there's a +1. But on the product side, well, there's a total charge of +2. And so what this indicates, this reaction, which is written incorrectly, what it's indicating is that as the reaction proceeds, you go from having a single positive charge to two positive charges. That means a positive charge popped into existence from nowhere. And so therefore this violates the law of conservation of charge. In this case, it's a pretty easy fix. It's not always easy, but in this case it's easy. We see that if a single copper metal reacts with two silver ions to produce copper 2 and 2 atoms of silver solid, then the problem's fixed, right? Because we have two positive charges on this side, two positive charges on this side, a single copper on this side, a single copper on this side, and two silvers on this side, and two silvers on this side, making this equation balanced for both mass and charge. And when dealing with redox reactions, it's often helpful to make sure that the reactions are balanced, obviously for mass. We've been doing that the whole time in chemistry, but making sure they're balanced for charge is very helpful. So we are now going to discuss how to balance redox reactions. So if I'm given a particular redox reaction and it needs to be balanced, this is a good procedure to follow, because redox reactions can be really particularly difficult to balance. And if you follow these steps, it's really helpful to figure out how to balance these reactions. So here's what you do. You first determine what's oxidized and reduced. Then you write two half reactions that describe the overall reactions. You balance the equation, the half reactions for mass. You balance them for charge. You multiply by a factor to get equal numbers of electrons. You add half reactions, and then you simplify. We'll go over a couple examples following these rules to give you the idea. Okay, let's try this particular reaction first. Okay, this is going to be the reaction that we're going to write. Well, first, we need to determine what is oxidized and what is reduced. Well, it looks like aluminum is going from oxidation number of 0 to an oxidation of +3. So it looks like my aluminum is oxidized. And that means the copper is going to need to be reduced, and it is, +2 going to 0. Now I'm going to write this as two half reactions. I'll write the reduction half reaction first. And this is how I'll do it. Copper 2 plus, that's going to need 2 electrons to go to copper 0, right? 2 plus and 2 electrons, that's going to give me an oxidation number of 0. Now we'll write the oxidation reaction. Aluminum solid, that's going to go to aluminum 3 plus, no charge, or no oxidation number total is 0 over here, so it means we're going to need 3 electrons over on this side. This total charge here, or oxidation number, ends up being 0. Well, notice that these two numbers of electrons don't balance, but we can make them balance by multiplying the whole reduction half reaction by 3 and the whole oxidation half reaction by 2. That'll give me 6 electrons here, 2 aluminum 3 plus, and 2 aluminum metal. On the top, that'll give me 3 solid copper, 6 electrons, and 3 copper 2 plus. So what I've done so far is I've written the two, sorry, I've skipped some steps. I've written the two half reactions. I didn't have to worry about balancing them for mass because I got a copper over here and a copper over here. Same with aluminum. I balanced them for charge by adding in electrons because, I had a 2 plus over here and a 0 over here. That means I needed to add an electron, 2 electrons here. In this case, I had a 3 plus over here and a 0 over here, meaning I needed to add 3 electrons to this side. The next step is I multiplied by a factor so that the number of electrons would equal. Multiplying this by 3 gives me 6 electrons. Multiplying this half reaction by 2 gives me 6 electrons. Then you add the half reactions. If I add these together, let's see what I'm going to get. I'm going to get 3 copper 2 plus 6 electrons. Let's see. That's going to go to 3 copper solid. And then down here, I'm going to get 2 aluminum solid. Goes to 2 aluminum 3 plus 6 electrons. Now if I add these together, I've got 6 electrons on the reactant side, 6 electrons on the product side. They can cancel, and what's left over is 3 copper 2 on the reactant side, 2 aluminum solid on the reactant side. That's going to go to 3 copper solid on the product side, and 2 aluminum 3 plus on the product side. This is now balanced for mass and charge. Check it out. 3 coppers, 3 coppers. 2 aluminums, 2 aluminums. And if I look at the total charge, this is 0. 3 times plus 2, that's plus 6. That's 0. 2 times plus 3, that's plus 6. This is balanced. Let's try a tougher one. Okay, first we got to figure out what's oxidized and what's reduced. Well, our manganese here is going to be a plus 7. And our sulfur, let's see, our sulfur and sulfate, I believe that's going to be plus 6. And our sulfur and hydrogen sulfate is going to be plus 4. Just to show you this one, because we've done this before, I want to show you this one. To show the oxidation number of sulfurs, plus 4. I've got a hydrogen, I've got a sulfur, and I have 3 oxygens that when I add together those oxidation numbers, they had better equal the charge on the substance. If I go through the rules, I'll end up assigning hydrogen a plus 1 and all of these oxygens negative 2s. You'll have to go back and revisit the rules to see this. So it's pretty clear that if I put a plus 4 here, this is plus 5, negative 6 gives me a total of negative 1. Alright, from this it's clear to see that the thing that is reduced is the manganese, right? And the thing that's oxidized, that's going to be the sulfur. That's the first step. I need to determine what was oxidized and what was reduced, and to do that I had to find the oxidation numbers of all the elements. Now I'm going to write both of those as 2 half reactions. Alright, so let's see. The reduction, that's going to be permanganate, is going to go to manganese 2. The oxidation, that's going to be hydrogen sulfite, that's going to go to sulfate. Alright. Got a balance for mass. So let's do the first one. I need to add water to the side requiring oxygen. Well, that's going to be this side over here, isn't it? See, I'm going to need 4. I need 4 waters because there's 4 oxygens. So let's see, plus 4H2O. I think that works. Now I got to add H plus to the side, or hydroxide to the side requiring hydrogen. Let's see, I'm going to need 8H plus over here, right? Because I need 8 hydrogens. 4 times 2. Yep, that's 8. Let's try this one down here. Balance for mass. Let's see, I've got to add water to the side that requires oxygen. Well, looks like I need a water over here, don't I? Yeah, because there's 4 oxygens over here. There's only 3, so let's add a water. Okay. Now I got to add H plus, or hydroxide, to the side requiring hydrogen. 1, 2, 3 hydrogens, so let's put 3H plus over here. Okay, so I've written my 2 half reactions. I've balanced for mass. Now I have to balance for charge. Let's see, over here I have a total of 8 minus 1. That's a plus 7 over here. Over here I have a plus 2. So that means I got to add 5 electrons on this side. 5 electrons, right? Let's make sure this works. 5 and 1 more negative. That gives me 6 negatives and 2 positives. That's a plus 2, isn't it? Yep, that's correct. And this makes me happy that I had to put the electrons on the reactant side because it's a reduction, right? The electrons are going into this. That makes sense. Now let's look at this. I've got a balance for charge. Let's see, I've got a total negative 1 over here. On this side, I have a positive, well, negative 2 and positive 3. That's a positive 1, isn't it? So how do I make a positive 1 balance a negative 1? I'm going to have to add 2 electrons on this side. Let's see if this works. 2 electrons and 2 negative, that's 4 negative, plus 3 positive. That's a negative 1 on this side and a negative 1 on this side. And it makes me happy that I added electrons over here because electrons are being lost. That's an oxidation. So this works. Woo! Okay, so I've balanced for charge. Now I need to multiply by a factor so that the number of electrons in each half reaction are the same. 5 and 2. Well, that means this whole thing is going to need to be multiplied by 5, and this whole thing is going to need to be multiplied by 2. Wow, let's do that. So I'm going to need 2 times 5, that's 10 electrons, plus 2 times that, 2 permanganate, 2 times 8H plus, 16H plus. We'll save the product side for later. Let's do the reactant side here. I'm going to need 5 hydrogen sulfites plus 5 waters. That's going to go to 2Mn2 plus 8 water plus 5 sulfate plus, this is still on the product side, right? Plus 15H plus 10 electrons. Wow. So I multiplied by the factor. Now I'm going to add these 2 half reactions together and simplify. I'm going to do some simplifying first. 10 electrons on the reactant side, 10 electrons on the product side. That should always be the case. If you haven't balanced electrons, you've screwed the whole thing up. Check this out. I've got 15H plus coming out, and I put in 16H plus. That means 15 of these is going to cancel 15 of these, and I'm left with just 1H plus. The other thing I can simplify is here. I'm putting in 5 waters, and I'm getting out 8, so I can cancel these 5 waters and end up getting just 3 water. 8 minus 5 is 3. That simplifies things quite a bit. Let's check it out. 2 permanganate plus 5 hydrogen sulfite. That's everything on the reactant side. That's going to go to 2 manganese 2 plus 5 sulfates plus 3 waters. And that, my friends, is a chemical equation, a redox equation, that has been balanced for both mass and charge. Let me just go check and make sure that's right. So I've got 2 negatives and 5 negatives for a total of negative 7 on this side. And on this side I have, 10 negatives Oh, somehow it screwed up. No. Oh, phew! My H plus. I forgot it. There it is. I thought I did everything right. Okay. So let's look at this again. 2 negatives and 5 negatives gives me a -7 plus this H plus. So I've got a -6 charge on this side. And on this side, I have, what's that, 10 negative, 5 times a -2, and 2 times a +2. You put those together, and you got a -6. So I know it's balanced for charge. Let's see if it's balanced for mass. 2 manganese, 2 manganese. How many oxygens? 2 times that, that's 8 plus 15. What is 8 and 15? 23. 5 times 4 is 20, and 3, that's 23. Whew, that's good. How many sulfurs? 5 sulfurs. 5 sulfurs. Awesome. How many H pluses? Don't forget this one this time. 5, 6 hydrogens. Look at that. 6 hydrogens. This equation is balanced for both charge and mass. All right, let's see if you recognize this particular redox reaction. Unbalanced. That's respiration, isn't it? This is actually a redox reaction. Now, I'm not going to show you this. You should be able to do this on your own, but if you assign oxidation numbers for all of these elements and all of these compounds, you'll find an oxidation number of 0 for carbon and glucose, and you'll find an oxidation number of +4 for carbon and carbon dioxide, and that shows you that glucose gets oxidized to carbon dioxide in the process of respiration. Also, you'll find an oxidation number of 0 for oxygen in the O2 molecule, and you'll find an oxidation number of -2 for oxygen in water, which shows that glucose undergoes oxidation and oxygen undergoes reduction in the process of respiration. Now we're going to try to balance this thing using the rules I've shown you. We've already done step 1. We've determined what is oxidized and reduced. I'm now going to write the 2 half reactions. So let's do that. Let's write the reduction first. That's going to be O2 is going to go to H2O. All right? And then the oxidation, that's going to be C6H12O6. That's going to go to CO2. All right. Now I need to balance each for mass. So let's see. I'm going to add water to the side requiring oxygen. Let's see. There's 2 oxygens here and 1 oxygen here. I need to add a water. That's pretty easy. 2 waters, right? That works. 2 oxygens and 2 oxygens. Good. I got a little trouble here because I've got 6 carbons. We better put a 6 here to make sure I've got 6 carbons on each side. That's going to be helpful. That's a step that this doesn't cover, but you should be checking for that. Anyway, I need to check which side needs oxygen and add water to it. I've got 12. Yep, that's right. I've got 12 oxygens. Over here I only got 6, so I better add 6 waters, yeah? I think that's right. Let me make sure. 6 and 6 is 12. Yeah, that works. Yep. Okay. Now I'm going to need to add H plus to the side that requires hydrogen. Well, let's see. There's 4 hydrogens, so I'm going to need 4 H plus over here, aren't I? I sure am. And then on this side, holy cow, what am I going to need? Look at that, 12. I'm going to need 24 hydrogens. That's a bunch. Holy cow. Yep, 12 and 12, that's 24. Okay, so they're balanced both for mass and not charge yet. So we got a balance for charge now. Let's do that. Well, it's neutral over here and 4 plus, so let's add 4 electrons to the reactant side of the reduction. That's good because the electrons are going into oxygen. That makes sense. And then over here, well, it looks like it's neutral over here, but man, I'm going to need 24 electrons to neutralize this, aren't I? I sure am. Okay, so we've taken care of that. I've balanced both half reactions for mass and for charge. Now I need to multiply by a factor to get my electrons in both half reactions equal. Let's see, I need 24 electrons out of 4. I got to multiply this whole side by 6, don't I? I sure do. And if I do that, I'm going to have, yep, 24 electrons. So I'm just going to write this equation. Let's see, it's going to be 6O2 plus 24H plus 24 electrons. 6 times that's 6. 6 times that's 24. 6 times that's 24 electrons. And that's going to go to 12 waters. Great. I'm going to add my half reactions and simplify. So let's add those two together. 24H plus on the product side cancels 24H plus on the reactant side. 24 electrons on the product side cancels 24 electrons on the reactant side. That had always better be the case. You have to balance electrons. And it looks like 6 waters on the reactant side will cancel 6 of these waters on the product side. So I'm ended up with 6 H2O over here. And hey, look at what you end up with. C6 H12O6 plus 6O2. That's everything on the reactant side. That's going to go to, oh, that's so satisfying, 6CO2 plus 6H2O. And we have shown how you can use redox chemistry to balance the redox reaction, that is respiration.